Hi, welcome to video 8.5D part 2, even more logistic.
Key things about logistic growth is the K will be positive and the Y will be less than or equal to A because A will be the maximum population. This is what the equation becomes. Once you solve the differential equation, that's what the graph looks like. But not in the book is logistic decay. What happens with logistic decay is K is less than 0, but Y is greater than or equal to K. A is a minimum instead of being a maximum. So the equation looks almost the same. This is A minus Y, that's Y minus A. Again, if you were to solve it, which will take many steps, the difference would be that this would be a minus here instead of a plus, and this would be a positive here instead of a minus. The graph, of course, will decay again. You'll notice here it's concave up, reaches a point of inflection, and then it's concave down as it approaches the horizontal asymptote. Here it's going to be concave down and then concave up after the point of inflection and approach the horizontal asymptote. So here what you have is it's increasing at a rapid rate, and then once it reaches the point of inflection, it's increasing at a decreasing rate. This is decreasing at an increasing rate and then decreasing at a decreasing rate. And again, the horizontal asymptote is going to be Y equals that famous A, which is the minimum possible. So here's an example. They're very wordy questions. A highly contagious pink eye is ravaging a school with population 900. The rate of infection is proportional both to the number infected and the number not infected. If 75 people were infected December 15th, call that T equals 0, and 250 had it by December 20th, how many people will have gotten it by Christmas Day? Okay, so because it says that the rate of infection, so that's your derivative, dy dt, is proportional to equals k times both the number of people infected, which is y, and the number of people not infected, which is A minus Y, and of course our A is our maximum population, which is 900. Now we know that this equation becomes this equation when you solve the differential equation, and we know that A is 900. So you'll notice the object of the game is to come up with an equation in Y and T, so I have to find B and I have to find K. Well, that's why they gave you this information. It says when T equals 0, Y is 75. So we'll plug that in. That's an initial condition at T equals 0. 75 people have pink eye. So Y is 75 when T is 0. Now T equals 0 is very convenient because this whole exponent becomes 0. Either the 0 is 1 and you end up with 75 equals 900 over 1 plus B, which will give you B is 11. So you can now rewrite this equation replacing B by 11. Now all that's going to mean is all we need to find now is the K. But then they give you another initial condition, which is that 5 days later, remember T equals 0 is December 15th, so T equals 5 is December 20th. So when T equals 5, Y equals 250. So now you're going to take our equation, which is basically this equation here, but we replace the B by 11, and then we replace T by 5 and Y by 250. You'll notice the only variable left is the K. Obviously, you're going to do that on your Texas Instruments. Do not round this. Your best bet is actually to store it in a memory location, K, for example. But if you round this too much, you're going to be way far off, okay? So if you were to graph this function now, putting this beautiful number here on 0 to 30, 0 to 900, you'd be able to see a good picture of that graph. Logistic growth worksheet. So I have a worksheet, if I can find it, right here that I have posted under the topics. There's some odds and there's some evens. I'm going to do some of the evens with you, and there's the answers to the odds. So if we look at number 46, in a limited environment where 1 million bacteria is the optimum number supportable, the rate of bacterial growth is jointly proportional to the number present and the difference between 1 million and the number present. That's logistic growth. If 500 bacteria are present initially, that word initially implies when T equals 0, Y equals 500 bacteria. And given that the rate of growth, now this is an interesting question, is 60 bacteria per minute when 1,000 bacteria are present, Find the mathematical model describing the number of bacteria, which is y, present as a function of the number of minutes, which is the time t, the bacteria has been growing. Determine how many are bacteria after 30 minutes, 1 hour, 90 minutes, 2 hours, 150 minutes. So show that the optimum number of 1 million bacteria is present within 7 hours. Okay, so we know it's a logistic growth. They've given us when t equals 0, y equals 500. The other thing they've given us is when dy dt equals 60, y is 1,000. So we know that this equation becomes this equation right here. So we know that the A is 1 million because they told us that was the population. And we're going to replace the t by 0. So when t is 0, y is 500. So I take y, replace it by 500. If t is 0, this whole thing is e to the 0, which is 1. So it becomes this equation. Solve that for b, you get 1999. So now we can replace our a by 1 million and our b by 1999. And again, we place our a by 1 million. And now we're looking for k. Now, the way to find k, they didn't give us another condition where when t equals this, y equals that. But what they did say, when y is 1,000, dy dt is 60. So I go back to my original dy dt equals k times y times a minus y. And I go, okay, dy dt is 60 when y is 1,000. And that, you can see, will give you the value of k, and then you'll get k here, and then you'll come over here and replace the k. It turns out to be this number right here, and then you take this equation right here and replace the k by that number. And now you have an equation in y and t, and that's the question: what is the mathematical model that represents this? Then find y when t is 30, because we did do this with minutes, so that if you store this in y1 in your calculator, you could just ask for y1 of 30, etc. In a community, this is number 50, in which 8 people are susceptible to a particular virus, the rate of growth of the spread of the virus was jointly proportional to the number of people who had caught the virus and the number of people who had not caught it. If 10% of those susceptible had the virus initially and 25% are infected after 3 weeks, what percent of those susceptible have been infected after 6 weeks? Okay, unfortunately here they can't pick a number, so we're stuck with A is A. We know by these words that the rate of growth is jointly proportional to the number of people who caught it and the number of people who have not. We know that's dy dt equals ky times a minus y. We've been told that when t is 0, y equals, so if 10% of those susceptible had the virus initially means at time t equals 0, the number of people who had it was 10% of those susceptible. And then it went on to say also, after 3 weeks, 25% had been infected. So y is 25% of A. So the question is, what percent are infected after 6 weeks? So we know that our logistic growth differential equation becomes this equation right here. So I'm going to initially it said the population was 10, the number of people who had the virus was 10% of that population A. So I replace y by 10% of A equals A over 1 plus B. And again, when t equals 0, the whole exponent is 0, e to the 0 is 1. Divide both sides by A, solve for B. So I can now rewrite this B as 9. Now it says when t is 3, y is 25% of A. So I replace y by 25% of A, and I replace t by 3. The a's cancel, and you can see now that we can get to this point right here where we have this equation right here. And that keeps going, and that keeps going, and that keeps going, and you keep slowly isolating. Now, I don't actually find the k. What I do here is I get it to the point where I have e to the negative ak equals the cubed root of 1/3. Because remember, this is my equation, a over 1 plus b, which we found, times e to the negative akt. Well, if I can replace e to the negative ak by the cubed root of 1/3, then e to the negative AKT is cubed root of 1/3 to the t. And then, where did I get t equals 6? Ooh, that's a great question. Number 50. Oh, what percent of those susceptible had been infected after 6 weeks? So we're going to let t equal 6 weeks, and then we go from there, blah, 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 simplify, and you get that y is half of a, which means it's 50.